Since March of 2023, we've been using a topical formulation we developed called Thioguard Lotion. Over this period, we have witnessed remarkable improvements, not only in children with autism spectrum disorder, but also in adults managing a range of complex conditions. It has become a tool we trust deeply, one that we use with our patients as well within our own families. The central ingredient in Thioguard is sodium thiosulfate. Our journey to discovering its potential was both unexpected and profound. It began with Jacob, a 9-year-old nonverbal boy with autism who, against all odds, directed us to this very molecule. Until that moment, sodium thiosulfate was not even on our radar. Yet, once we began to apply it in clinical practice, the results were striking. Now, more than 2.5 years later, Thioguard has touched the lives of hundreds of families, maybe more, offering improvements in areas once thought resistant to change. In this video, I want to share not only the story of its origins, but also the science, the mechanisms that may explain why we continue to see such encouraging outcomes. If you would like to listen to an interview I did with the parents of Jacob, please visit our Rumble channel and look for this video and learn how we discovered this incredible molecule. Sodium thiosulfate, or STS, is a compound with a surprisingly broad therapeutic profile. It has been FDA approved since 1939 for the treatment of cyanide poisoning in the IV form, and it carries GRAS status, generally recognized as safe. Its long clinical history underscores both its safety and versatility, and today it is available in multiple formulations for different medical applications. At the core of its therapeutic actions are 3 powerful mechanisms. First, glutathione recycling. STS reduces oxidative stress by sparing NADPH, thereby supporting the enzyme glutathione reductase and regenerating reduced glutathione. It also serves as a sulfur donor for cysteine synthesis, feeding into the glutathione biosynthetic pathway. Beyond that, it participates in enzymatic reactions such as those catalyzed by rhodinase and sulfur transferases, helping to regenerate thiol groups that are critical for cellular defense. Second, heavy metal binding. Sodium thiosulfate forms complexes with a variety of toxic metals. With nickel and platinum, it creates moderately stable complexes, a property leveraged in children undergoing platinum-based chemotherapy. It can also complex with mercury, although less strongly than classic thiol chelators, and with arsenic and antimony, though those complexes are weaker. This capacity to sequester and neutralize heavy metals adds another dimension to its protective potential. Third, cyanide metabolism. Through the action of the rhodinase enzyme, STS facilitates the detoxification of cyanide. It converts cyanide into thiocyanate, a less toxic metabolite that is water-soluble and readily excreted in urine. This pathway has saved countless lives in cases of cyanide exposure and remains one of the foundational applications of the compound since 1939. But beyond these core mechanisms, sodium thiosulfate exhibits an impressive range of protective effects. It has been shown to be neuroprotective, cardioprotective, and even protective against ischemia reperfusion injury. It also supports renal health, inhibits the formation of methemoglobin to improve oxygen transport, and bolsters rhodinase enzyme activity within mitochondria. Taken together, this is not simply an old antidote for cyanide poisoning. Sodium thiosulfate represents a multifaceted therapeutic molecule, one with the ability to recycle antioxidants, bind toxic metals, neutralize cyanide, and provide systemic protection to the brain, heart, kidneys, and beyond. Over the last 2.5 years, we have received hundreds of messages from parents who have used the Thioguard Lotion, and it remains our most powerful detoxification support. You can find more messages on this link down here below, And so let's dive into the mechanisms in a little bit more deeper. This is one of the most critical insights into the mechanism of sodium thiosulfate because it reveals how glutathione is formed, how it functions, and how it must be regenerated once it has done its job. Glutathione serves two indispensable roles in human biology. First, it binds and neutralizes toxins, primarily in the liver. Second, it acts as a major intracellular antioxidant, reducing free radicals and thereby lowering inflammation. You can see this illustrated here. The GST gene encodes glutathione as transferase, which attaches glutathione to toxins for detoxification, while the GPX gene encodes glutathione peroxidase, which reduces reactive oxygen species. Chemically, glutathione is a tripeptide composed of 3 amino acids: cysteine, glutamate, and glycine. Among these, cysteine is the rate-limiting component, and it derives from homocysteine. Homocysteine is a fascinating molecule because it sits at the heart of the methylation cycle, while also serving as the key precursor for cysteine, which in turn allows for glutathione synthesis. Here's how the detoxification process unfolds. When a toxin enters the liver, GST helps attach glutathione to it. In doing so, glutathione donates a sulfur atom, or an ion, making the toxin less reactive, more water-soluble, and therefore excretable via bile, urine, or stool. But once glutathione donates that sulfur ion, it is left in an oxidized form. In that state, it is inactive, like a car without fuel, and cannot neutralize another toxin until it is recycled back into its reduced or available form. This recycling step is carried out by glutathione reductase, or GSR, and requires NADPH, the cell's primary electron donor. NADPH is essential not only for glutathione recycling, but also for reducing free radicals, as you see here in the right upper side. And it reduces free radicals such as superoxide. And here lies its hierarchy. NADPH is preferentially used to fight acute oxidative stress, to put out the fire, before it is used to refill glutathione. Now consider what happens in autism. Many parents describe a specific trigger, often vaccination, after which their child condition deteriorates. One plausible mechanism is that the intense inflammatory response consumed so much NADPH that little remained for glutathione recycling. The result is a chronic state in which glutathione remains oxidized and inactive, leaving the child trapped in ongoing oxidative stress and inflammation. Under normal physiology, the body can generate sodium thiosulfate, which helps resolve this paradox. STS reduces oxidative stress by sparing NADPH, supporting glutathione reductase in regenerating active glutathione. It also serves as a sulfur donor, facilitating cysteine production and feeding directly into glutathione biosynthesis. Our claim is that in many individuals with autism, the capacity to generate thiosulfate is impaired. This explains why studies consistently find low available glutathione or reduced glutathione and high oxidized or used glutathione in autism, demonstrating a bottleneck in the recycling process. This imbalance directly intersects with the methylation cycle. Normally, methionine is converted to S-adenosylmethionine, SAM, the universal methyl donor. Under oxidative stress, as glutathione is consumed and the oxidized glutathione rises, the body diverts homocysteine towards transsulfation to make more cysteine and glutathione instead of remethylation to regenerate more SAM. This diversion lowers the SAM to SAH ratio, reducing methylation capacity. The consequences are profound. A reduced methylation capacity impairs DNA synthesis and repair, diminishes histamine breakdown, and disrupts the metabolism of neurotransmitters such as dopamine and adrenaline. This explains why simply giving a child glutathione can backfire. If recycling is not restored first, the excess glutathione is rapidly oxidized, further increasing the oxidized glutathione. This worsens the bottleneck, suppresses methylation, and can provoke surges in histamine, dopamine, and adrenaline, symptoms sometimes mislabeled as a detox or Herxheimer reaction. In reality, the child is caught in a redox methylation trap. The lesson is clear. The recycling process must be corrected first. Only after restoring glutathione homeostasis and NADPH balance does it make sense to stimulate greater glutathione production. I will return to this principle again in a subsequent section. Cyanide is a rapidly acting cellular poison that exerts its lethal effects by targeting the final step of mitochondrial respiration. In the electron transport chain, electrons are passed along to cytochrome C and finally delivered to cytochrome C oxidase, which is complex 4, where oxygen is normally reduced to water. Cyanide binds tightly to the iron center in cytochrome C oxidase, blocking oxygen from binding and accepting electrons. As a result, electron flow backs up. Cytochrome C becomes trapped in its reduced state, and the entire electron transport chain stalls. This halts ATP production despite the presence of oxygen, producing a state of histotoxic hypoxia in which cells are unable to use oxygen, leading rapidly to organ failure and death if not treated. This mechanism, by the way, starts the cell danger response, and we do not necessarily believe that blocking the cell danger response is a smart idea, despite some findings that it can help with symptoms of autism acutely. Just think about this for a moment and judge for yourself. The cell danger response is there for a reason. It signals danger. That's like deactivating your fire alarm sensors in your house to prevent the annoying noise when there's thick smoke. Anyway, when cyanide is affecting the mitochondria, a lot of free radicals or superoxide is generated, and that chops off heme from red blood cells, and the ferric iron that's released is forming methemoglobin, which by itself is toxic. However, it is actually the most powerful chelator for cyanide. So ferric iron, the Fe3+, is binding cyanide, which forms cyan methemoglobin. And at that stage, the body is trying to make water-soluble thiocyanate, which can be excreted through the kidneys. Now, what's required in this step are two things. One is sodium thiosulfate, and the other one is rhodonase, which is an enzyme that is in the liver, also in the brain, that catalyzes that reaction. Now, when we have problems, for example, with low iron states in children, or if we have an absence of thiosulfate, or we have a defect in the rhodonase enzyme, there's a backup mechanism of how cyanide can be bound. Now, since cyanide likes to bind to iron, it likes to bind another metal, and that's cobalt. And we have a lot of cobalt in vitamin B12. Most of it sits in the form of hydroxycobalamin in the liver. And so the secondary detox mechanism, if the other one has failed, is to bind 2-hydroxycobalamin to form cyanocobalamin, which is a form of vitamin B12 that also gets excreted to the kidneys. So, when we measure vitamin B12 levels in children, we often find that they have very high levels of vitamin B12. The reason for that is not that we're giving our children too much B12, but rather that the cyanide liberates the B12 in the liver, binds it, and makes it circulate in the blood, which is not usable by the body. So in fact, it actually means that the child needs more B12 rather than restricting vitamin B12. So there was this doctor, Dr. Derek Lonsdale, who was a physician and researcher who has written extensively on autism, vitamin B1 deficiency, and metabolic aspects of disease. He identified cysteine as central to glutathione metabolism, and he passed away on May 2nd, 2024 in Cleveland, Ohio, at the age of 100. Interestingly, he proposed in one of his papers that one of the abnormalities that he found in the urine of kids with autism was a decrease in the concentration of thiocyanate. And these authors hypothesized that this might be due to decreased activity in the enzyme rhodinase that converts toxic cyanide ions to non-toxic thiocyanate. Now, we hypothesize a deficiency of thiosulfate. However, it is not unlikely that both of these mechanisms may be at play. For one, a problem with the rhodinase enzyme, and two, a problem with the generation of thiosulfate. Now, of course, we wanted to see if it's true, if children affected with autism have elevations of cyanide, and we needed to find a way to prove that. Now, first, I called into the emergency department of the Detroit Medical Center. I talked to an attending, and I said, hey, how would I determine if somebody has cyanide poisoning? Do we just draw blood and measure it? And he said, no, we don't do that. He said it would require you to flash freeze or spot freeze the blood, and then you would need to send it through a sequencer, which is a very tedious process, and nobody does that because most cyanide cases are acute. You need to act fast. Nobody has time for extensive testing. So they actually just measure the lactate levels that form. Lactate forms in a cell that cannot produce energy due to anaerobic glycolysis. And so people usually die of lactic acidosis, of a lowering pH. And so we found these testing strips, which very accurately measure to the parts per million the concentration of free cyanide in water. And we thought, well, if it detects cyanide in water, why wouldn't it detect cyanide in urine or maybe saliva? And so we tested about 20 kids, and it's a very cheap test. And so what we found was pretty profound. Now, first off, we tested the urine, and everybody's urine was negative for any cyanide, which would make sense. And what we found in the saliva is these very significant elevations of cyanide, as you can see here. The more blue this testing strip turns, the more cyanide is present. The upper neurotypical control was actually my own, and as you can see here, we have several patients with very profound blue results. On the very right, you see a significantly affected boy with autism, and we tested his neurotypical sister, who was not even close to the blue that he was affected with. So another critical finding here, that actually cyanide very much and very likely is involved in the pathophysiology of autism. Last but not least, I want to touch upon another lotion we have developed called Glutathione Genesis. Now, as we have discussed, you really should start with the recycling process before you introduce new glutathione. So you don't want to increase that bottleneck, because that might inhibit methylation and you will see reactivity. So usually what we want to do is introduce the Thioguard and allow the glutathione to regenerate, which will decrease inflammation and free up the NADPH, which then eventually, hopefully, will start by itself again to regenerate the glutathione. Once you have reached that point, and we usually say, about 2 weeks in after using the Thioguard lotion, you may want to introduce the Glutathione Genesis. Now, in this lotion, we added NAC, which is cysteine, as well as magnesium, which is highly neuroprotective. And so with that is that we push the glutathione production at the same time reducing inflammation, freeing up NADPH, and having the whole glutathione cycle spin a little bit faster. You can use these lotions in conjunction, although we do recommend you apply these lotions on different areas on the skin. Do not mix them together. You don't want the reaction to happen on the outside. You want to happen in the inside. And so, generally speaking, you can go down with the use of Thioguard after some time and just use the Glutathione Genesis more often. I really hope you enjoyed this summary about our Thioguard and Glutathione Genesis lotions. If you have any questions, please direct them to contact@researchedelements.com. If you would like to purchase one of our lotions, please go to researchedelements.com/shop. Thank you.